there are lots of composite numbers. And we tend to like to talk about how composite numbers are related to each other. And two relationships that end up being important once we get to fractions are greatest common divisor and least common multiple. So, thinking about our friends the factors, what are the factors of 12 and 18? Well, we have 12 is 1, 2, 3, 4, 6, and 12. And I didn't put in my curly braces, so we'll go back and add some really rough looking ones. And those are my factor sets for 12 and 18. Now, which factors do they have in common? Well, they both have a 1, they both have a 2, they both have a 3, they both have a 6. So they have those factors in common. And so which of those is the largest? The 6. And so we call that 6 the greatest common factor, because the greatest common factor, the GCF, is the largest. Ooh, that's a combination of both the and largest, is the largest of the factors common to both or more, right? You could do this for 3 numbers. And so if you look at any list of factors for any 2 numbers, there will be guaranteed to be a largest, right? Because you can list every factor of any number. And so you find the largest that's common to both. Sometimes, like is the case of, say, 3 and 5, let me write this. If I have 3, which only has the factors 1 and 3, and 5, which only has the factors 1 and 5, the greatest common factor there is 1. So the GCF, the largest common factor might be 1, and that's okay. And numbers like that, which don't have any factors in common, we call coprime. You don't need to know that for this class, but it's not a bad thing to have heard that word. So 3 and 5's greatest common factor is 1. Now, let's look at multiples of 12 and 18. So we've looked at factors, now we'll look at multiples. Well, 12 is 12, 24, 36, 48, 60, 72, and so on. 18, 36, 54, 72. So what multiples do they have in common? Well, they have the 36 in common, and they have the 72 in common, and they'll have more. So which of those multiples is smallest? Well, it's the first one. It's the 36. And so that 36, because it's the smallest number such that both are factors, if we want to use our language there, because 36 has 12 as a factor, and 36 has 18 as a factor, and it's the smallest number for which that's the case. But we call it the least common multiple, because it's the smallest multiple common to both. So, how we found all the factors. How did we decide that we could find them efficiently? Well, in Tyrese's example, we saw as soon as we found that turning point, we could stop. And similarly, we'd like to find a way to find the GCF and LCM efficiently, particularly when we're working with really big numbers. So, yes, 12 and 32, not the largest numbers, but let's write their sets, or let's write all of their factors. So 12 is 1 times 12, 2 times 6, 3 times 4, and then we get to 4 times 3. And so those are all of our factors of 12. And notice that's my strategy for writing sets of factors is I'll put my braces really far apart, and then I'll fill them in. Well, 32 has a 1 times 32. 2 16s. Do we have a 3? No, we do have a 4 times 8. 8, 16, 24, 32. 6 times 5 is 30. Not going to work. 7 won't work. 8 back to 4. That's our turning point. And so we know we're done. We both have a 4. And so now that we found all of them that are common, and so let me give these sets some names just so I can refer to them. So we'll call this the divisors of 12. That's supposed to be a D. And we'll call this other one the divisors of 32. Well, if we take their intersection, divisors of 12 intersect with divisors of 32, we get 2 and 4. And because we're interested in the greatest common divisor, all we have to do is these are our common divisors. And that one's the greatest. And so 4 is the GCD. So the GCD of 12 and 32 is equal to 4. And similarly, if we want to find the intersection of sets for the multiples, and let me go ahead and clear a little bit of space. Sorry, I accidentally made screen go black. So those are our common divisors and our greatest one. Now, if we want to write the multiples, and I'm going to just go ahead and give these sets names from the beginning. The multiples of 12, 12, 24, 36, 48, 60, 72, how much higher do we have to go? 84, multiples of 32, 32, 64, 128, 256. Whoa, I skipped way too many. Does anyone know what I did there? I started doing powers of 2 instead of multiples of 32. 64 plus 32 is 96 plus 32 is 98, 128. And it keeps going, right? And so I'm going to do one more up here for 12, and you might already know why, but 84 plus 12 is 96, and you can keep going there. And so again, we're looking what's common to both the intersection at the multiples of 12 intersected with the multiples of 32, and we get the set containing the 96, and then there will be more, but that's the smallest. And so we say the LCM of these two numbers, 12 and 32, is 96. And so we call that the intersection of sets methods because we write our sets with all of our divisors and intersect them, and all of our multiples and intersect them, and we see precisely what happens. Now you're asking, I still have to find multiples here. Can I use this fact about primes to make this somehow better? We can. And for that, we'll do what's called the prime factorization method. And so here what we'll do is we're going to find the GCD and LCM using the prime factorization method. So first, let's write the prime factorization of 12. Well, 12 is, I'll do my scratch work over here. I can take a 2 out, I get a 6. I take a 2 out, I get a 3. 3 is a prime, and so its prime factorization is 2 squared times 3. Same with 32, 2, 16, 2, 8, 2, 4, 2, and 2, so 2, 4. So we have 1, 2, 3, 4, 5 2s. 32 is 2 to the 5th. Now, the GCD is the greatest common divisor. Well, they both have at least one 2. And in fact, they both have at least 2 2's. So we can take a 2 2's or a 4 out of both. We can't take a third 2 out because 12 only has 2 2's in it. And we can't take a 3 out because a 32 doesn't have a 3 in it. And so our greatest common divisor is 2 squared, or 4, which if we go back, oh, I erased it, we also had 4. Relatedly, if I want to find the least common multiple, every factor up here needs to be represented. So let me erase this unnecessary red triangle that I drew. It has to have every single factor in it. Because for 32 to divide it, for it to be a multiple of 32, all 5 of these 2's need to be there. Now, if there are 5 2's there, 2 2's will still divide it, right? Because 4 divides 32. And so we need all of those 2's to be there. Now, for it to be a multiple of 12, we need a 3 to be there. Now, 32 doesn't have a 3, but if I multiply it by 3, it's still a multiple of 32. So I need to include my 3. And now, if I take the product of these 2 times 2 times 2 times 2 times 2 times 3, enter, I get 96. What did we say our least common multiple was? 96. So if we find our prime factorization, we have 2 rules. The greatest common factor is all of the factors that are common to both. But the least common multiple has all of those common factors and any that didn't get accounted for, right? Like that 3 that was left over in the 12, or those 3 more 2's that were left over in the 32. And then I have one more method I would like to show you, in particular because I think this method is efficient for working with large numbers. And it goes back to our friend, the slide that we use for factoring. So suppose I want to find the LCM of 1080 and 1200. Well, I can essentially use a slide to find the factors of both. Well, I know there's at least a 10 in there, right? There's 108 and 120. I can take at least another 2 out. That'll be 54 and 60. There's another 2 in there. We have 27 and 30. We can take a 3 out, and we get 9 and 10. 9 has just 2 3's in it. 10 has a 2 and a 5. And so there's nothing else we can find. Now, these aren't all primes, right? But we could break them down. 2, 5, 3, 3, 2, 5. Now along the left here, these factors, and I'll just circle the primes, represent all of the factors that are common to both. And now our rule from the last slide was the greatest common factor are all the factors common to both. So the GCF then is 1, 2, 3 2's, 2 cubed, times 3, times 5. And we said the LCM had to be all of the ones that were common, and any of these other ones. Let me pick a different color, because I think this will be easier to see. So our LCM is, that's impossible to read, our LCM, I don't want blue either, I've already used it. Struggle. LCM is all of the ones that are common and all these ones that are left over. So I have 1, 2, 3, 4 2's, 2 to the 4 times 1, 2, 3 2's, or 3 3's rather, 1, 2, 3 3's, and 1, 2 5's. So we have 5 squared. 2 to the 4th times 3 cubed times 5 squared. And that's our GCF and LCM. And why does this work? Well, just like we talked about last time. Oh, and so there's another set of slides, which more or less should have shown you. The left one should show you the same, more or less, for the numbers of interest. We have 6, 10, 2, 10, and 9. We have a 6, 10, 2, 10, and 9. They're all accounted for. And I said 6, and you're like, well, where's the 6? There's the 6. So 6 times 2, 6, 10, 2, 10, and 9. And then the other one's there for you to practice on your own. And why does it work? Because the ones along the left, those factors, are the common ones, and the ones at the bottom are those that are left over. And we had our two rules that our GCF is all the common factors, and our LCM is all the common factors and all of the ones left over. Now I do want to make a note. In the homework, it says to use the Euclidean algorithm, and that's really the slide method. So let me write that. The Euclidean algorithm is different, but I'm not going to be covering that, and I forgot to change the directions in the homework. And so this will be in an email. But use the slide method. So they're not the same, but use the slide method instead of the Euclidean algorithm in the homework. And so there'll be a problem that says use the Euclidean algorithm to find the certain amount of, or it'll say use the Euclidean algorithm to find the LCM and GCF. And since I didn't cover the Euclidean algorithm, because children aren't going to be using the Euclidean algorithm prior to grade 8. They're going to be using the slide method, and so that's why I chose to introduce that here.